Hello everyone, welcome to lecture 20 of the online course Modern Display Technologies Flat Panel Display. Today's lecture will be on liquid crystal materials, dielectric constants, viscosity, elastic and the figure of merits. So, here is the lecture outline. We will have some recap from lecture 19, we will talk about the refractive indices and the birefringence. Then we will discuss the dielectric constants, we will focus on the Meyer theory, the delta epsilon and the polar groups. We will talk about the positive delta epsilon liquid crystals, something like the fluorinated compounds for twisted nematic, in-plane switching and TFT LCDs. We will also talk about the negative delta epsilon liquid crystals like the lateral difluoro for the vertical alignment displays, and then we will focus on the dual frequency liquid crystals, talk about the crossover frequency and fast switching. Then we will focus on the rotational viscosity gamma 1, study its temperature dependence and the molecular design, invoke the elastic constants K11, K22 and K33 and see it from the mean field theory and the device impact point of view. And the final figure of merit will do the comparison of the liquid crystal materials for the response time. So, here is a brief recap from the previous lecture and the transition to this lecture. So, the key results from lecture 19 were that the refractive indices basically connect to the molecular structures to the liquid crystal optics. The Works model gave this as the refractive index, where alpha was the molecular polarizability. So, this was basically giving the macroscopic index. The extended Cauchy gave the refractive index in the extraordinary and ordinary, same as here, where it is given in this form, which is basically considering the practical dispersion model at any wavelength. Then there were 3-band model lambda naught, where sigma to sigma star the transition happens at 120, then lambda 1 around 200 nanometer, lambda 2 around 282 nanometer for the 5 CB, basically for the pipe to pipe star band transition. And then we have also seen the Heller model, where delta NT was given as delta NO 1 minus T by Tc whole to the power beta, where the average value of the n is basically A minus Bt. So, this is basically a 4 parameter model for the extraordinary and ordinary refractive index, but as a function of temperature. Now, what the optical properties that determine in a device? The first thing is the phase retardation, which is capital gamma given by 2 pi d delta n divided by lambda. So, this basically determines the gray level tuning range and the dark bright states. Also, the cell gap d needs to be chosen so that it satisfies gamma equals pi, that is half wave. So, that basically gives you d equals lambda by 2 delta n. So, what you see that larger delta n will give you smaller d, that means the cell gap is less. So, you will get faster response. So, larger is the birefringence, means the difference between Ne and No, faster will be the response. So, what we will still need to fully specify a liquid crystal device? So, another parameter is how much voltage to apply. So, dielectric constants, we have seen that there is one along the parallel, along the perpendicular. So, that is named as epsilon parallel and perpendicular, and their difference is given as the delta epsilon. Now, how fast it responds, that also matters. So, that is basically coming from the rotational viscosity gamma 1 and the elastic constant, that is K II. It can be K11, K22 or K33 depending on the type of deformation. And then which material is the best choice? So, you have to compare the figure of merit, which is calculated as K dot delta n whole square divided by gamma 1. So, with that, now let us move on to this discussion of the dielectric constants. where we will be invoking this Mayer theory to talk about the birefringence, the dipole moment, orientation angle and order parameter, right. So, dielectric constants basically determine the threshold voltage VTH and the direction of the liquid crystal orientation, whether it is towards or away from the field, okay. And the sign delta epsilon basically determines whether the liquid crystal is suitable for twisted pneumatic or in plane switching. So, that is when it is positive, it is either twisted pneumatic or in plane switching, or vertical alignment where this delta epsilon will be negative. So, that those modes can be determined. So, here is the most important section for understanding how the molecular design determines the display mode compatibility. So, you can compare the twisted pneumatic versus IPS versus vertical alignment. So, let us talk in terms of the Mayer physical picture. Okay. So, the liquid crystal dielectric constants basically influence the operating voltage, electrical resistivity and the electro-optic response time. So, once again, what is the origin of this dielectric constant? So, this are mainly determined by the molecular dipole moment, that is mu, dipole orientation angle theta, orientational order parameter S, molecular polarizability alpha and finally the temperature. Now, what you see in the Mayer mean field theory, okay, the dielectric constant parallel to the director, that is called epsilon parallel, can be written as N H F and then average of alpha parallel plus F mu square divided by 3 kT times 1 minus 3 cos square theta into S. So, what is this F here? That is the Onsager reaction field. Capital N is basically the molecular packing density. H is here the cavity field vector given as 3 epsilon divided by 2 epsilon plus 1. The epsilon that you see here is basically epsilon parallel plus 2 epsilon perpendicular by 3. That means, it is basically the averaged dielectric constant. Theta is the angle of the dipole moment mu to the molecular axis and S is basically the order parameter. So, all these things are coming from the physical picture, like you can consider a rod shape liquid crystal molecule with a dielectric moment mu at an angle theta to the long axis. So, when the electric field is applied along the director, okay, you can that is basically for the epsilon parallel measurement, right. So, the permanent dipole basically wants to align with electric field, but the thermal energy will resist. The induced polarizability along the long axis is nothing but your alpha parallel, okay, that also contributes, right. So, what you see that overall the epsilon parallel is large when mu is along the long axis, that means your theta is small, and that is the case when alpha parallel is also large. The other case can be when the electric field is perpendicular to the director, that is giving you epsilon perpendicular, where dielectric constant is basically seen perpendicular to the director. Okay. So, here the dipole contribution is much smaller because the dipole alignment with the field is less efficient, and that is why in this case the induced polarizability, which is alpha perpendicular, that will be much smaller than alpha parallel for the rod shaped molecules. So, you can basically approximate this using this particular formula. Okay. So, it is very basically having the same form. Okay. So, you can also calculate the delta epsilon, where epsilon parallel minus epsilon perpendicular gives you delta epsilon. So, you get this. Okay. So, this just by subtracting these two. So, what you see here that there are basically two contributions. One is basically the polarizability difference. So, this itself is small if it is for non-polar liquid crystals, and the second one is dipole moment mu and the orientation angle theta, that plays an important role. Now, for the case of a vertical alignment cell, the threshold voltage is basically depending on the dielectric anisotropy and the band elastic constant. So, you can obtain the threshold voltage VTH as pi square root of epsilon naught K33, that is basically the band elastic constant for the vertical alignment liquid crystals. So, K33 divided by delta epsilon. So, epsilon naught is the permittivity of free space and magnitude of delta epsilon is basically the amount, or you can say the magnitude of the dielectric anisotropy. So, what you see here, a lower threshold is good, then you can have faster switching at lower voltage. So, your device becomes operatable at lower voltage. So, that can be achieved by increasing the delta epsilon, or you can reduce this K33, or you can do both at the same time. However, when you reduce this elastic constant K33, that basically weakens the restoring torque, and that will eventually increase the response time. So, better you only focus on increasing this delta epsilon part. Now, liquid crystal molecules can be non-polar or polar. Okay. So, for the non-polar components, mu equals 0 and their dielectric anisotropy is generally very small. So, delta epsilon is typically less than 0.5, and in this case the delta epsilon is mainly determined by the differential molecular polarizability, that is your alpha parallel and alpha perpendicular, right. And for the polar molecules or polar compounds, your delta epsilon strongly depend on mu, dielectric orientation angle theta, temperature T, and also the applied field frequency. Okay. Now, if a molecule contains several dipoles, the effective dipole moment will be their vector sum. Now, what is the effect of this dipole orientation? Now, you can see that for theta less than 55 degree, the effective dipole is mostly along the molecular axis. Therefore, this 1 minus 3 cos square theta term is negative. That means your delta epsilon will be positive. So, you are getting a positive delta epsilon. That means you must operate in the twisted nematic or IPS mode. When theta is greater than 55, the effective dipole is basically transverse to the molecular axis. That means mostly along the short axis. Okay. Now, in this case you will see that 1 minus 3 cos square theta term is positive. That means your delta epsilon comes out to be negative, and that is typically the VA mode, vertical alignment mode, and that is typically common for the polar groups. So, here you see that you are getting a magic angle which is theta equals 55 degree, which is basically the cos inverse of 1 by root 3. So, at this particular angle your 1 minus 3 cos square theta term becomes 0. That means the dipole contributes 0 to the delta epsilon permittivity difference. Okay. So, let us now look into some of the commonly used polar groups in the liquid crystal compounds and study their dielectric properties. So, you can see the fluoro group F has got mu equals 1.5 D, cyano group has that Cn mu equals 3.9 D, and isothiocyanate group, that is NCS, has got mu equals 3.7 D. Okay. Now, if you consider the fluorinated that is this one, the fluorinated liquid crystal, they has moderate dipole moment which we have discussed. So, this fluorinated compounds generally provide high electrical resistivity, low viscosity, and good visible region performance. Okay. And the strong fluorine electronegativity compresses the electron cloud, and that reduces the birefringence. Now, one important thing here, you are seeing D, that D basically stands for dBi, which is the standard non SI unit used to measure the electric dipole moments, right. So, if you want to convert it into the international systems of unit, that is the SI unit, you can have 1 D will be typically 3.33564 times 10 to the power minus 30 coulomb meter. Okay, that is how you can basically convert those. So, what we understand that strong fluorine electronegativity compresses the electron cloud and that reduces birefringence. Therefore, fluorinated compounds are suitable for visible displays requiring delta n to be equal to 0.1. So, how do you get high birefringence liquid crystal compounds? So, basically they are required for infrared applications where higher birefringence can compensate for the longer wavelengths. So, the typical requirement is delta n greater than 0.3, and the birefringence can be increased by extending the pi electron conjugation length. So, what are the two common approaches followed here? The one is elongating the molecular core using structures such as toluene or terphenyl, okay. And the other approach would be to adding electron acceptor groups such as CN or NCS, that is cyano or the isothiocyanate groups. Now, here you can compare the properties also. See, for the cyano based liquid crystal compounds, they have large dipole moment 3.9 d, okay, dBi. So, the strong localization of the charge in the carbon nitrogen triple bond, that basically produces strong intermolecular interactions, and these interactions basically promote dimer formation. Therefore, this kind of cyano based liquid crystal mixtures generally exhibit relatively high viscosity. On the other hand, the NCS based liquid crystal group, they have dipole moment of around 3.7 d. So, the charge localization here is slightly weaker than that happening in CN group, and so they will have weaker intermolecular interaction. So, as a result, you can understand the dimer formation is suppressed and you will get lower viscosity. Okay. However, the longer pi electron conjugation of the NCS group basically produces higher birefringence. So, what do you get from this NCS based liquid crystal compound? You get higher birefringence, lower viscosity and better suitability for the infrared applications. Now, let us compare the positive and the negative delta epsilon liquid crystal compounds. So, we have already seen that the positive anisotropy liquid crystals are typically used in twisted nematic and IPS displays. So, the fluoro group can be placed in the para position, that is position 4. So, there you can have this angle theta less than 55 degree, that means you will get the delta epsilon positive. And if you have single para F compound, there you can get delta epsilon around plus 5, and adding lateral groups in position 3, 5 further can raise this anisotropy to plus 10. So, what are the advantages of this F group? You can get high resistivity, which is essential for TFT LCD to prevent flickering, which is a disturbance for the displays, and also it gets low viscosity. However, this F group also comes with some drawback. The first thing is that it basically lowers the birefringence because your electron clouds are compressed, and you can get delta n in the range of 0.07 to 0.12 only. Okay. As a result, if you look for OCF3 groups, they have similarly good resistivity plus even lower viscosity. So, that can be useful for improving the response time. However, replacing the middle cyclohexane with phenyl can actually allow improving this delta n from 0.07 to 0.12. So, that is like extended conjugation. You can also achieve the melting point control, where the lateral fluoro substitutions basically lowers the melting point. So, that basically means the intermolecular association is getting weak. On the other hand, we have already seen the Negative delta epsilon liquid crystals are basically used for vertical alignment displays. There the dipoles in are in lateral positions 2, 3, okay, and theta will be greater than 55, that means you are getting the delta epsilon less than 0, that is negative. So, you can use the lateral difluoro group. So, the vertical dipole components basically add and horizontal cancel. So, you get the net dipole moment, net lateral dipole, that gives you delta epsilon to be negative around -4. When you have alkoxy group in adjacent, that basically enhances the negative delta epsilon. So, that is because the oxygen has lateral lone pairs contributing here, okay. And typically the negative values range from -3 to -8, and however there is a viscosity trade off. So, more lateral groups will have larger moment of inertia and that will have larger viscosity. So, what are the challenge here? Increasing this magnitude of the permittivity anisotropy, that requires more substitutions, and that comes at a cost of viscosity penalty, which will essentially lower the response. So, what you see by this comparison is that both types must have high resistivity for TFT LCD, where rho is typically greater than 10 to the power 12 ohm centimeter to prevent image flickering. Now, let us look into this dual frequency liquid crystals. So, this represents a elegant solution to the fundamental liquid crystal switching asymmetry. Okay. So, here the earlier cases, the electric field can pull the liquid crystal into alignment, but cannot push it back, okay. And the restoring force is purely elastic, which was limited by the elastic constants and the cell gap. So, when you have this DFLC, it basically solves this by using a different frequency to create a field that actively repels the alignment. Okay. So, dual frequency liquid crystal basically has frequency switchable delta epsilon. Okay. So, the unique property here is that the delta epsilon is positive at low frequencies and it becomes negative at high frequencies. So, there is a crossover frequency Fc at which your permittivity difference is basically 0, and that is typically a few kilohertz. So, what you see at F less than Fc, your delta epsilon is positive. So, liquid crystal aligns with the field and you can use low frequency AC voltage to turn on. On the other hand, at frequency greater than Fc, your delta epsilon becomes negative. So, your liquid crystal aligns perpendicular to the field. So, you can use high frequency AC voltage now to turn off. So, that is like a active decay. So, what is the benefit? You get fast response time and you do not need to wait for the elastic restorant force alone. Okay. So, the standard liquid crystal, the turn off time is basically given as tau off, that comes from the viscosity and the elastic constants like gamma 1 d square divided by k pi square. Okay. So, it depends on the liquid crystal elasticity and it is slow near the threshold. So, when you have DFLC, you are basically applying high frequency voltage burst for turn off also. So, you are actively driving the liquid crystals back. So, your tau off reduces dramatically. So, in this case, both the rise and the fall time can be shortened. So, this is essential for fast displays such as gaming, 3D and medical imaging. So, you can see DFLC mixture composition here. Okay. So, in this particular figure shows the frequency dependent dielectric anisotropy of a positive liquid crystal mixture A, okay, whose delta epsilon is basically frequency dependent, as you can see on the top, and it is negative here, okay. And then the one you see here is basically the DLFC mixture curve. So, this is the one that is negative, this is the one that is positive, and this is the one that is basically the mixture. Okay. So, a DLFC mixture is basically composed of some positive with some ester group and some negative liquid crystal compound. So, the positive component ester group, you can see it is delta epsilon is basically positive at low frequency, that is at DC, okay, and as the frequency increases your delta epsilon gradually varies, right. So, you get delta epsilon to be frequency dependent. On the other hand, if you consider the negative component, that the delta epsilon of the negative component is fairly remaining flat and it is frequency dependent. So, when you mix it, you basically get this kind of thing where the crossover, the FC comes around 9.2 kilohertz, that is this particular middle solid line. So, what is the trade off here? This DFLC mixtures have a higher viscosity and narrower nematic range as compared to the standard liquid crystals. Now, we will discuss about the rotational viscosity and the elastic constants. So, the dynamic properties, these are the dynamic properties that govern the liquid crystal response time. So, rotational viscosity has the temperature dependence and it plays a crucial role in deciding the LCD's response time, that is the viscosity. Okay. The response time of a nematic liquid crystal device is basically linearly proportional to the viscosity. So, the viscosity controls the rate of liquid crystal director reorientation and hence the device response time as well. And typically there is a temperature dependent term in this viscosity. So, your gamma 1 is basically B dot S is B into S into exponential E by kT. So, B is the proportionality constant that depends on the molecular shape, dimension and the moment of inertia. S is the order parameter, E is basically the activation energy of rotation, and this is Boltzmann's constant and the operating temperature. And this order parameter can be approximated as this S equals 1 minus T by Tc whole to the power beta. Beta is a material parameter that comes from the Heller exponent beta that is used for birefringence, and T here in that case is valid when T is not too close to the clearing temperature Tc. Okay. So, the combined form where gamma 1 T basically combines the molecular order and the thermal activation. So, it basically takes this kind of a form. We are basically combining these two. So, what you see here that there are basically two competing effects. One is that your S decreases with T, okay. So, that basically reduces your gamma 1, and you see also that there is a exponential E by kT that decreases too. So, that reduces gamma 1, right. So, what happens that with increase in temperature T, your net gamma 1 is basically dropping rapidly. So, what are the key practical rules for rotational viscosity gamma 1? So, the empirical rule says that for every 10 degree rise in temperature, gamma 1 nearly drops by 2 times. Okay. So, that means it is a huge temperature sensitivity, and the molecular design rules for low gamma 1, that means faster response, is that the linear molecular shape will have less static hindrance during rotation. So, it will have lower inertia, lower moment of inertia. So, you will have lower viscosity. Shorter alkyl chain also will have lower moment of inertia, but if it is too short, it may have higher melting point. That means, it may have solubility issue. Even length alkyne chains within homogeneous even N chains have slightly lower gamma 1 than odd N. So, you may have this odd even effect. And another important thing is that to avoid the CN polar group, because strong CN phenyl dimers will give you high viscosity. So, you basically should prefer the NCS or the fluoro groups. Finally, all this comes down to the liquid crystal cell response time calculation. So, for vertical alignment display MLC 6608 at 20 degree centigrade, gamma 1 is given like this, that is the parameter K33, and if you consider the cell gap as 4 micron, the response time comes out to be around 17 microsecond. This is how it is computed. Tau naught equals gamma 1 d square divided by K33 pi square. So, you plug in all the values, you get 17 millisecond. Okay. So, this matches experimental observations of the vertical alignment cells, where it was reported that the response time is between 15 to 20 millisecond at room temperature. Now, these are the three elastic constants that are concerned in the liquid crystals K11, K22 and K33. These three elastic constants basically govern the restoring torque when a liquid crystal is deformed from its equilibrium alignment. Okay. So, the mean field theory for elastic constants says that Kii is basically A into S square. A is the proportionality constant depending on the molecular shape and the intermolecular potential. S is the order parameter. So, you have Kii that is proportional to S square. So, the elastic constants basically decrease rapidly near the transition temperature Tc. Now, what is the ordering of the elastic constants for most liquid crystal compounds and mixture? You will see that the band constant K33 is greater than K11, that is the splay 1, greater than K22. So, K11 is for the band, that is in IPS, typically in the homogeneous cells. K22 is for twist, that is in twisted nematic, in 90 degree twisted cell, and K33 is for band, that is for vertical alignment, which is in the homeotropic cells. So, the threshold voltage using appropriate elastic constant can be obtained using this formula. You see VTH equals pi square root of epsilon naught Kii over the difference in the magnitude of the anisotropy. So, here for Va you have to put K33, for Friedrichs plate transition in homogeneous cell you have to use K11, and if you want to calculate the Tn twisted nematic threshold you have to enter K22. So, response time scaling that you obtain from this formula, that is tau equals gamma 1 d square divided by K pi square. Now, based on this you can understand that the tau of the vertical alignment will be the lowest one, followed by the IPS, followed by the twisted nematic. That means, because vertical alignment has largest elastic constant, it will have the fastest elastic restoring, shortest response time, and on the other hand twisted nematic will have the smallest elastic constant. So, the slowest response time. So, the effect of lateral difluoro substitution on the elastic constants also show that lateral F groups basically increase the molecular width. So, that will increase the splay and the band coefficients, that is K11 and K33, but that will also increase the moment of inertia. So, you will get higher viscosity. The temperature dependent study shows us that Kii is proportional to S square, but this falls to 0 at Tc, that like second order behavior, and this is why the threshold voltage also changes with temperature. So, this VTH is basically proportional to this, which is also proportional to, because the square root of K that is proportional to S, that is the order parameter. So, now we can do the figure of merit comparison for the liquid crystal molecules for the response time. Figure of merit provides a single unified metric to compare liquid crystal materials for response time optimization. So, what is that figure of merit here? So, you can choose K dot delta n square by gamma 1. So, K is basically the appropriate elastic constant based on the type of mode you are operating. Delta n is basically the birefringence, and gamma 1 is basically your rotational viscosity, right, all at the same temperature, right. So, if you have the larger figure of merit, that means this material is the best for fast switching with low driving response, right. So, what is the physical meaning of this FoM? This FoM basically links all the parameters, okay, liquid crystal parameters. So, tau min can be obtained as 1 over FoM. So, that is basically coming from d square divided by FoM into pi square by lambda square. So, if you consider a fixed cell gap d and a fixed wavelength lambda, larger FoM means shorter response time. The temperature dependence in the FoM also comes from the material model. So, your FoM can be temperature dependent, where it basically combines the temperature dependence coming from the order parameter that you have seen earlier, and it can be written like this. So, what you want? The optimal operating temperature TOP that can happen when the derivative of the FoM with respect to temperature becomes 0, and that is when the TOP is around Tc times 1 minus 3 beta k Tc by k plus the other terms. Okay. So, you can see that the figure of merit is maximum when this happens. TOP is approximately equal to Tc minus 3 beta k Tc by epsilon, that is for the vertical alignment liquid crystal MLC 6608. So, you see that the operating temperature comes out to be 70, okay, that is around 20 degrees below the Tc, which is at 90. So, how do you compare different materials? For same FoM target, you can do the trade off between the delta n, the elastic constant k and the gamma 1 and choose your material. So, if you want to summarize the discussion today in terms of dielectric constants, viscosity, elastic constants and a figure of merit, we understood that the dielectric constants where delta epsilon basically determines the VTH and the liquid crystal mode. We have also seen the Mayer theory that allows the parallel and the perpendicular permittivity to be determined by the molecular dipole moment, the orientation angle theta and the order parameter s. We have seen theta negative gives you positive birefringence, or you can say positive anisotropy in permittivity. So, that is for twisted nematic and IPS. For positive theta you get vertical alignment mode. Then F group has shown high resistivity, low viscosity and modest delta epsilon, whereas the CN mode they have shown high delta epsilon, but high viscosity. So, if you can see NCS, that is where the compromise is. We have also talked about DFLC, where the delta epsilon switches sign at the crossover frequency Fc. So, this basically enables fast switching. We also discussed about rotational viscosity, the origin of this, and we have seen that it halves every 10 degrees centigrade temperature rise, and the linear liquid crystals have lower gamma viscosity, whereas the dimers can cause high viscosity. So, you can prefer the fluoro or the NCS group. And this is a comparison between the different elastic constants. Okay. So, you can we have also seen the vertical alignment has got the fastest response time and twisted nematic has got the slowest one, and the threshold voltage basically depends on this thing. So, if you want to lower the threshold voltage, you can either decrease this constant or you increase this. Okay. Finally, the figure of merit was calculated as k delta n whole square divided by gamma 1, where the response time was seen to be inverse of this figure of merit, and figure of merit has a temperature maximum at TOP, that is around 20 degree below the Tc, okay, that you have already seen. So, you can approximate it like this. So, it tells you that this MLC 6608, the figure of merit basically peaks at 70 degree centigrade, which is typically operating at 35 to 40 degree centigrade, already 60% better than the room temperature. Okay. So, with that we conclude this lecture. If you have got any query regarding this, you can drop an email to this email address mentioning the course name and the title on the subject line. Thank you.